Good afternoon, my name is Chen, and today I'm going to talk about the novel translation to infer the reference path from calling context, which can help the developers to quickly locate the root cause of bugs. My professor is Harry Xu, and this is a joint work with other colleagues, Kan, Zhiqiang, Qiren, and Zheng Dong. So in postmodern debugging, context is a piece of very important runtime information. Broadly, there are two types of context information: calling context and reference context. So calling context represents a chain of call sites when the bug occurs. The reference context in object-oriented programs is a chain of heap references leading to the object accessed in the bug. While the calling context is widely used and reported by most of the debuggers, we found that reference context is also very, very useful in many debugging tasks. To motivate that the reference context is useful, I'll show you a real example. I know the font is kind of small, but I will, try to help you to dive in. So this is an example from the Eclipse plugin. That plugin is used for comparing two files and report the differences, but it suffered from a memory leak problem. So these bugs involve three methods: run compare, open compare, editor on page, and use value. So the key idea here is that this input object was allocated in the line 2 and was last used in the and was added to the navigation history object and never get deleted. This bug was reported to us by a memory leak detector called SLAY. SLAY is a staleness-based detector. It reports the most stale object. In this case, stale reports that this input object is a stale object, which was allocated in the second line and was last used in the line 14. In the final report, SLAY also gave us the last use side of this stale object. That means the place where the stale object got last read or write, along together with the call stack, the calling context, in which this last use occurs. However, for the developers, in order for the developers to understand the bug and fix the bug, it is critical to know that the root cause is actually in the open compare editor on page. That is, this navigation history object was cached in a global editor object and never get deleted. So, but this open compare editor on page method is far away from any method that reported in the call stack and the last use side. So by just having this call stack, it is insufficient for the developers to understand the root cause. However, if we can additionally report this reference path, the heap structure, we can help the developers to understand that which object is actually referencing this leaky object. Then in this case, it's this navigation history object 9, then we immediately know the root cause. Reference context is not only useful in memory leaks, but it also very useful in many other problems. For example, databases, illegal state bugs. For example, for the databases, the existing database detector only report the RECE object. For example, here the detector report that this object O is a RECE object, but still we are unclear that why this object is RECE and how to fix it. However, if we can have the reference path, we know this hash map is on the reference path, then we immediately know this bug is due to an improper use of the data structure. Actually, this hash map is not thread safe. We should use a thread safe hash table instead. Now we understand that reference path is useful, but you may ask, how can we get it, right? So currently, the only way of getting the complete reference path is to do the heap dumps. It is very difficult because the objects in the heap do not carry backward pointers. For example, if you want to get the object, the little object down there, you have to perform the whole heap dump. Even if the number of the objects of interest is small, you still have to do the whole heap dump. This obviously has a very large overhead. And here we did an experiment of getting the reference paths by performing the heap dumps. On the benchmark of the Capo 2006, we modified the memory leak detector SLAY to report 20 leak objects for each benchmark, and along with these calling contexts, and then perform the heap dump. The top is the total execution time, and the bottom is the slowdown. For the heap dumping, as we can see, the minimum execution time is around 2 minutes with a 13 times slowdown, comparing the execution without heap dump. And the maximum execution time is over 6 hours with a 7,800 times slowdown. This is obviously very time consuming. As already saw, the overhead of dynamically getting the reference paths, it is very time consuming. Alternatively, you may think of doing the static analysis. However, if you just perform a generic static analysis without any guidance, then number one, you will have a very large search space that makes the static analysis very unscalable. Number two, all the paths, most of the paths we end up finding will be unrelated to the particular event. So we want to give our static analysis a little guidance. For example, we can use the calling context recorded together with a dynamic event to help us to track a small subset of the reference paths that are truly related to the dynamic event. Basically, we know that the existing dynamic analysis tools will record the calling context for us. And if we can utilize this calling context and fit it into our static analysis framework, then number one, we can get more relevant results. And number two, we can dramatically reduce the search space. The goal here is to use the cheap dynamic analysis to capture some runtime information and fit them into our static analysis framework, which is going to compute the set of reference paths for us. The information captured by the dynamic analysis includes 3 pieces of information: calling context C for the particular event, and object O involved in the event, and variable V points to the O. These 3 pieces of information are not new requirements. They are already captured by most of the existing dynamic analysis tools. To achieve that goal, given the program, we first turn that program into a special graph representation called interprocedure symbolic point-to graph. Then based on that graph, we perform our new CFL-Reachability formulation called Constraint-Guided CFL-Reachability formulation which can take the calling context as input and guide our CFL-Reachability computation over the graph. And this computation eventually will provide the reference paths for us, which can help the developers to perform the postmodern debugging. I'll briefly talk about the symbolic points-to graph here. I tell you how to get the symbolic points-to graph for the code of the previously mentioned Eclipse plugin. So the key idea here is for each method, we first compute the intra-procedure symbolic points-to graph. How do we do that? First, we create a bunch of symbolic nodes to represent the objects that are not visible within this method. And then we perform a local points-to analysis. Then after that, the locally resolved points-to graph becomes to the intra-procedure symbolic points-to graph. And we do this for all the methods. After we having this all the intra-procedure symbolic points-to graph, then we can connect them trivially by connecting the symbolic nodes at each call sites through the function call edges and return edges. That's how we end up having a inter-procedure symbolic points-to graph. for the code that is listed on the left. After talking about the graph we use, now I'm going to talk about the constraint we used for the traversing on the graph. Recently, there are a lot of researchers have used CFL-Reachability for various alias and points to analysis. We also found it is very useful for our translation framework, so we modify it and adapt it to our framework. But before I talk about the constraint-guided reachability problem, I'll first talk about the general CFL-Reachability problem. CFL-Reachability mostly is a balanced parentheses graph reachability problem. Each edge in that graph was annotated with a label. So eventually, what we want to find is the path whose labels contains balanced parentheses. For example, for the pointer analysis here, we perform our CFL-Reachability computation over two languages, M and H. Language M guarantees that function calls and returns are properly matched for context sensitivity. And language H guarantees that the value that is written into that field will be retrieved from the same field. The balanced CFL formulation is widely used. However, in our framework, we're not only tracking the balanced parentheses and brackets. In addition, because the unbalanced parentheses reveal the calling context, and the unbalanced heap accesses reveal the reference path, then we want to modify these two balanced language M and H to let them allow certain unbalancedness so that we can use them to guide our computation over to find this unbalancedness for our translation purposes. The new grammars for these two unbalanced language, M tilde and H tilde, can be found in our paper. Recall that the inputs of our static analysis captured by the dynamic analysis includes three pieces of information. Their calling context, C, for a particular event like a bug, object O involved in the bug, variable V points to the object O, and our goal is to look for paths whose labels are strings of these two unbalanced intersection of these two unbalanced language M tilde and H tilde. And all the paths start from this variable V and ends the object O prime. O prime is another object that may directly or transitively reference the object O. How do we do that? As I already mentioned, we have some constraints. The first constraint is the string constraint. We want to use the calling context C to help us to prune the search space of the path with the unbalanced heap accesses. And the second string is the path constraint. We have to make sure that the paths reported by the static analysis have to pass O. The reason for that is variable V point to object O is a runtime behavior captured by the dynamic analysis. We know this must happen. So that's the reason we want to make sure all the paths have to go through O. These are the two constraints we will check when we perform the CFL-Reachability computation. Finally, this unbalanced heap accesses from object O to O prime will form a reference for a context for object O. Because of the limit of time, I'm not going to try to tell you how exactly to find this this path, but here I'm going to show you one valid path. So for example, recall the Eclipse example introduced before. The memory leak detector sleigh reports three pieces of information. The first one is the stale object O2, and second one is variable V inserting, and the third one is a calling context. That is a call of the use value method in line 4, and together with the last use side. And we have a path from this variable inserting and ends as another object O9, which is a navigation history object referencing the stale object O2. And this is the calling context. And we know this is a valid. We know this is a valid path. How do we do that? How do we know that? First of all, we get the path string from that path, which look like this. And then we perform a set of checks over this path string. For example, the first check is for the string constraint. We want to know whether this calling context is a prefix of this path string. In this case, calling context line 4 is indeed a prefix of the path string. And the second check is for the path constraint. We want to know whether object O2 is in the path, which is also the case. Then we can conclude this path is a valid path. After that, we can retrieve the unbalanced open brackets, like the unbalanced heap accesses from this path. Here they are array element and array. And after that, we find a reference path for O2, which goes from object O9, which is the navigation history object, to object O21, and finally go to the cell object O2. To implement our analysis, we modify the calling context app trees to get the calling context. Calling context app tree is a dynamic infrastructure that can efficiently profile the calling context. And we use the suit framework to implement our static analysis. Later, we modify the ISPG representation and implemented our new constraint-guided CFL-Reachability over the ISPG. The benchmarks we target on is the couple 2006 MR2. To evaluate our static analysis, we look at two metrics. The first one is precision. The second one is the usefulness. To understand the precision, we modify the JOX RVM to use the heap dumps as a ground truth. After our static analysis did the inference, we compare them with the result obtained from these dynamic heap dumps. And for the usefulness, we want to understand whether our static analysis result can truly help the developer to make a better sense of the bugs. We look at two real client analysis, memory leak detector SLAY and data race detector PACER. After comparing the result from our static analysis with the heap dumps, we found that the report reference paths can surely help the developers to make a better sense of the bugs. So the results shows that our analysis is fast, precise, and useful. For example, on average, it takes about 13 seconds to answer a translation query. And to understand the precision, we look at two aspects: the number of the reference paths and the length of the reference paths reported by our analysis. After the analysis did the inference, we compare the result with the dynamic counterpart, the heap dumps, and we find that our static analysis only produced 2% more and 13% shorter reference paths. For the number of the reference paths, the less the better. For the length of the reference paths, the longer the better. So that means the result of our static analysis is very close to the heap dumps. And we also performed a set of usefulness check on the benchmarks over the two real client analysis. And we find that they can truly help the developer to understand the bugs. The detailed case can be found in the paper. And finally, we designed an efficient translation algorithm that can statically infer reference paths from calling context. And more importantly, our framework would work as a general framework for a class of interleaved language reachability problems. For example, given the constraint of one string, one language, we can answer what the other language will look like. With this as my conclusion, I'm happy to answer questions.
Thanks. That was really interesting. So I wanted to know, you talked a little bit about the usability, the utility to the. Can you tell us a little bit more about that? How do you actually evaluate that, and what do you measure, and what do the results look like?
It's like like I taught, we have a set of usefulness case study. So we just use these two real client analysis, and to report the three pieces of dynamic information, and then we manually check, whether by just using these three pieces of information we can, understand this bug very quickly. And it turns out it's very difficult. But after we let the static analysis to perform the inference, then we look at the reference paths. Then we know that this reference paths will help our understandability for these bugs.
But you looked at it, right? It wasn't.
Yeah.
You
Yes.
didn't do a study with users. It was you looked at it, right?
Yes,
Is that right?
manually checked in the paper.
Okay.
Yeah.
All right. Let's thank our speaker one last time.
Thanks.